Okay, good morning everybody. So today we're going to talk about section 2.4. 2.4 covers concavity and something else. Okay, mainly just concavity. So we're going to talk a little bit about concavity, and we're going to give ourselves a more rigorous definition for what it means for the graph of a function to be concave up or concave down. Because so far what we've done is just kind of this wishy-washy, well, if it looks like an N, then it's concave down, and if it looks like a U, then it's concave up. And that's not a very good way of defining things. So we're going to give a better definition for that. But first, we have this warm-up problem. So if you're at home watching, recommend that you pause the video and give this a shot yourself, and then unpause when you're ready to see the solution. So let's see here. We've got A, B, C, D, E, F, G points on this graph of this function, which is the graph of f of x itself. And we're supposed to find out whether f and f prime are greater than 0, equal to 0, or less than 0 at these points. So first of all, who can tell me what it means when f prime is greater than 0? What does that mean for our function? Yeah?
Does that mean the slope's positive?
Yeah, it means the slope is positive. So what would it look like on the graph? Just going up. Yeah, exactly. So if we're going up, then our function is increasing. If our function is increasing, then we say that the first derivative is larger than 0. Likewise, if this first derivative is less than 0, we should expect the graph of f of x itself to be decreasing. In other words, going down. Okay? All right. So let's take on A. First, I think we can all agree that the value of f at A is less than 0. I put in a less than because, well, it's below the x-axis, right? Why don't we do all the points with just f, and then we'll move on to f prime. So B, it's right on the x-axis. We're going to get an equals. C, it's beneath the x-axis, less than. D, we're going to have below the x-axis, less than. E, we're on the x-axis, equal to. F, we are above the x-axis, greater than. And G, we're above the x-axis, greater than. That should be pretty much second nature by now to fill out that part. All right, the derivatives, I think, the more important part of this problem. Who wants to help me with A? What do we think for A? Increasing, decreasing? Should it be, yeah, Andrew?
Increasing?
Yeah, we think increasing, so f prime should be?
Greater than?
Yeah, greater than 0. All right, next up, we've got B. What do we think?
Equal to?
Equal to. I like it. The reason it's equal to at B is if we were to draw the tangent line at this point, it would look like it's horizontal. Okay? The slope of a horizontal line is 0. So, if the derivative is equal to the slope of the tangent line at that point, then the derivative will also be equal to 0. All right, next up we've got C. What do we think? Less than, greater than? Yep.
I said 0 is greater than.
For at C?
Yeah, because the slope is going down, right?
Yeah, slope is going down. But we said that the slope of our function is going to be negative at this point, right? Would you agree with me? So if the derivative represents the slope of our tangent line, we should have a negative number in here, which means that at C we should have less than 0 in here. Does that make sense? Okay. How about at D? What do we think at D? Yes, Kevin. Equal to again, right? We've got another tangent line coming in horizontally. Okay, so that's equal. E? Yeah, Ellie? Greater than. Why not 0? Positive slope, right? So in other words, we shouldn't get tripped up just because the point is on the x-axis. It's true that f at this point is going to be equal to 0. Doesn't necessarily mean that our derivative has to be 0. So we've got greater than 0 here. And at f, it looks like we're going to have another horizontal tangent line, so I'll put equals. And then at g, it looks like, once again, we're going down. So at g, I'm going to say less than. Okay, going down means decreasing, means derivative less than 0. Okay, any questions about the warm-up? Okay, sweet. So let's give a more reasonable definition of what it means for a function to be concave up or concave down. So before, we had this rule. We said if you look at the words concave up and concave down, then we said that this is kind of what it looks like for it to be concave down, or this U here in the word up is kind of what it looks like for it to, yes?
Nice direction.
Yeah, of course. Yeah, you don't need to ask. Okay, so if it's looking like a U, then it's concave up. If it's looking like an N, then it's concave down. And that's sort of a wishy-washy definition. So now we're going to give a more reasonable definition. We also had before, I just want to remind you of this. F prime greater than 0 meant, that's why I'm putting an arrow here. By this arrow, I mean implies that f itself is increasing. F prime less than 0 implies f is decreasing. Okay, so that's another thing that we want to talk about. So now we're going to describe the concavity of a graph using not this first derivative, but the second derivative. So if we take some function and we do its derivative, we get another function. If we do the derivative of that function, we call that function the second derivative of f, and we write f double prime. And f double prime greater than 0, this implies that f prime is increasing, which in turn implies that f itself is concave up. Likewise, if we have f double prime less than 0, this tells us that f prime is decreasing, which tells us that f is concave down. Okay, so now we've got a kind of a more rigorous way to check whether something is concave up or down than by just looking at the graph. I think a lot of students struggled with determining where things were concave up on the exam problem. So let me kind of dive into what these two definitions really represent graphically. So I'm going to make an extra page here so we can do some drawing. Add page. We don't like that paper, do we? We like this paper. Okay. So let's draw. Well, let's not draw like that, first of all. Let's draw a straight line. Let's draw the graph of a function which is concave up. We'll do the most simple one, something like a parabola is concave up. Okay? And what I want to be able to show you guys is why is it true that f prime increasing means that f itself will be concave up. That's what I want to describe for you guys, okay? So if I look at this function here and I consider what's happening to f prime as we move from left to right, I'm going to draw in a bunch of tangent lines. Okay, so first my tangent line looks like it's going pretty much straight down. That's a negative slope. And then as I move along, my slope becomes less and less negative, right? Until we get to 0, and then my slope is 0. And then I move to the right, and my slope is now becoming positive. Okay? So as I move from left to right, the slope of my tangent line is increasing. Do you all agree with me? Okay? And that really characterizes what it means for the purple graph to be sort of bending upwards. Okay? As we move from left to right, we're bending in an upwards direction. Okay? So if I draw a bunch of tangent lines and they look like this, you know, if I was playing like Line Rider or something, I don't know if kids still play Line Rider, right? My dude would come here. He'd be on his little sled. And what these lines mean is I'm going to start bottoming out and then I'm going to start going up. Okay, and I'm going to have this nice U shape. All right, likewise, if my tangent line slope is decreasing as I move from left to right, what's that going to look like? It'll look something like this. Right? These will be what the tangent lines look like. And if my tangent lines look kind of like that, then I'm going to expect the graph of my function to maybe look something like this. Okay, and that would be a concave down situation. Okay, so as I move from left to right, at first my slope is very positive, and then it's becoming less positive, then it becomes 0, and then it starts becoming negative. This is what it means to say that f prime is decreasing. Is this intuition relatively clear? Okay. I think this is a much better way to characterize concavity for functions, as opposed to just say, look at it and does it seem like it looks like it's bending upwards. It's a little bit wishy-washy for my taste. Okay, so that's what we've got. So now we're supposed to figure out the concavity of our original warm-up problem. Let me see if I can like let's see if I can copy that picture down here. First of all, let me get rid of all this crap. Okay, I think I should be able to copy and then, oh yeah, beautiful. Okay, so now we're supposed to figure out whether our function is concave up or concave down at each of these points. Okay, so I'll do the first two and then maybe I'll have you guys help me with the rest. So at A, remember, there's two kind of ways that I can characterize whether we're concave down or up. I can think about, okay, well, it does kind of look like we're bending downwards, so it's concave down. I could just say that. Or I could literally look at the tangent line at this point. It looks like it's going like that. And then find some point very nearby, right? Maybe this point here. Let's do it with a different color. We'll do it with pink. So some point very nearby, but to the right. And check what's the, okay, well, that's not a good tangent line, is it? Maybe this is a good tangent line. Okay, and check, is the slope of the tangent line nearby and to the right larger or smaller? In our case, the slope is not quite as extreme, meaning that as we moved from left to right, the slope decreased. So if I go back to my definition and think about what does the slope decreasing mean, that's exactly to say that f prime is decreasing, which is exactly to say that we are concave down. So if I was going to describe the concavity of f at the point A, I would say that it is less than 0. Now at B, I'm going to say the exact same thing, because if I look at my tangent line right at B, it looks like this, and shortly thereafter, we're pointing down, right? Which means that my slope of my tangent line decreased again. So I'm still going to say less than 0. And now here's something that I want to be careful. Oops, that was supposed to be the eraser. Here's something that I want to be careful about describing properly. It can be a little bit tricky to find the points where our concavity switches. It's really easy to see where our first derivative changes sign. Our first derivative changes sign at either a peak or a valley, right? That's when our function goes from being decreasing to being increasing, or from being increasing to being decreasing, right? It's relatively simple to just look at the graph and see those points. However, it's a little bit more vague to look at a graph and immediately point out what we call the inflection point, which is what we call the point where f double prime is actually equal to 0, and then we change concavity. Okay, and that's exactly what's happening at C here. Okay, to the left of C, we are concave down, and to the right of C, we are concave up. Okay, so that's telling us that C is an inflection point. i.e., f double prime of C is equal to 0, right? If we're less than 0 immediately before and greater than 0 immediately after, then we have to say that at that point we're actually equal to 0. So for this part, I'm going to say equals to 0. Let me ask, are there any questions about the inflection point? That really confused me the first time that I came across it. Yeah, Andrew?
Since on both sides, you said, which makes it...
Right, so it's kind of the point which divides. If I were to look at this, well, okay, shoot, that was supposed to be, say, concave down. If I look at this line here, and I consider what's happening to the left of that line, visually, it looks like it's bending downwards, right? If you were to think about, if I were, say, here driving a car, okay, here's my car, I'm not an artist. If I was driving my car, before I get to C, which way would I be turning the steering wheel, left or to the right? I'd be turning to the right, right? And then at C would kind of be the moment that my steering wheel was straight, perfectly straight, okay? And then which way am I turning my steering wheel after I pass C, when I'm going here? I'm turning to the left now. Okay, so concavity is kind of like, which way is the car turning? Whereas if we're using the car analogy, increasing or decreasing is like whether I'm driving north or south. Okay, if I'm at first I'm driving kind of north, but I'm bending towards south. I'm turning my car. Okay, and then at B, I start driving south. Okay, and then at C, I straighten out my steering wheel, still driving south. And then at D is when I've turned my steering wheel to the left, and then now I'm starting to go north again, after I pass D. Do you guys find this analogy helpful? Okay, so just remember that this concavity stuff is really about which direction the steering wheel is turned. And the increasing and decreasing is more about which direction is the car actually driving. Okay? If I turn my steering wheel, it's going to take me a little while to turn around, right? So for the first while, I'll still be kind of traveling in a northwards direction. Okay, I think that's about... Did that answer your question? So yeah, immediately before this point, we're concave down, and immediately after, we're concave up. That's what it means for there to be an inflection point at that point. Okay. Oh, one thing that I want to remind people of. I have office hours today. From, I think, 11 to 1. And it's the MTC link. Remember, these links are all on Blackboard. You can just go there and click the one that says Fridays, 11 to 1. Okay. All right, so let me erase some of this stuff that's on the picture here, and then kind of ask you guys about the last few. All right, so now we want to know, what is our concavity at the point D? So I'm interested in this point right here. Who can help me figure out what that concavity is? Yeah, Alice?
It's concave up.
It's concave up, and what's your reasoning? It's okay if it's just visual. Okay, just visual. We're bending upwards, so Alice says concave up. So what do we think for the sign of F prime?
Greater than.
Yeah, greater than 0. Okay? In other words, I'm turning my steering wheel to the left. Okay, if you want to use the car analogy. All right, how about at E? What do we think about E? Yasmin? Very good. E is another inflection point. Because if I was driving my car, the moment that I got to E would be the moment that my steering wheel was exactly center. Right? All right, and how about F? After I pass E, which way am I turning my steering wheel? To the right or to the left? To the right, which means that I'm concave down, which means that F double prime, remember this, at E it was equal to 0, F double prime at F is going to be less than 0, exactly, thank you. Okay, you guys are getting the hang of this. And how about at G? What do we think? Yeah, it still kind of looks like less than 0. It doesn't look like we've exactly straightened out yet. It looks like maybe we would, I don't know, you kind of have to interpret. Maybe if it did go like that, I don't know. It's a little bit hard to say. Less than 0 is what I would feel confident putting there. Okay. Any questions about this first problem on concavity? Okay. Let's move on to problem number 2. Okay, now we're going to get a little bit abstract with it. Okay, maybe this is a good time to split into groups. So let's have these 3 in group number 1. You guys can work on C. Group number 2 being Mia's row, well, just Mia, I guess, and Aaron's row. You guys can work on B. Everyone else past Ryan, you guys can work on A. And we'll give this a shot. So what we're trying to do here is just interpret this information and try to sketch the graph of a function which satisfies these qualities. Would anybody like a little bit more time? Feel okay? All right, group one being Alice, Sam, and Andrew. Would anybody like to volunteer their paper for scrutiny for the benefit of the class? Or if you're not comfortable sharing your actual paper, you can tell me what it looks like.
Were we doing A or C?
You guys were doing C. I suppose we should start with the other side of the class, shouldn't we? Let's have somebody from group 3 and 4. Anybody who would like to volunteer their paper? Kevin, thank you. I'll come grab it. I'll get it right back. Thank you, kindly. All right. So Kevin has kindly volunteered his paper, so we're going to try to replicate his drawing here and see if we agree. So we're doing part A, and we've got f of 2 larger than 0, f prime of 2 greater than 0, and f double prime of 2 is less than 0. Okay? So this is the graph that Kevin drew on his paper. Looks like it's going through this point right here, and it's bending kind of like this. Okay, what do we think about that? Why don't we go through the three pieces of the problem? Thank you very much, Kevin. Let's go through the three pieces. So first of all, we've got f of 2 is larger than 0. Do we agree that this graph satisfies this first property? I think so, right? Because we lie above the x-axis, right? Okay, how about the second property? What does it mean for f prime of 2 larger than 0? What does that mean for our graph of our function? Yeah, Andrew?
It's a positive slope.
Positive slope. Okay. So exactly right. And I think that this certainly qualifies, right? If we were to draw the tangent line in here, it would definitely have a positive slope. So I think we can agree on f prime of 2 is larger than 0. About f double prime of 2 is less than 0. What does that mean for the graph? Yeah, Kevin?
Should have been concave down.
Okay, Kevin answered it, found his own mistake. So it should have been concave down. Okay, so this is the property that wasn't quite satisfied by Kevin's original drawing. How would you fix it?
Like rotating it so it's.
Yeah, sure. We could, for example, rotate it by like 180 degrees, and then it would look something like this. Okay? And I think that is what it should look like. Whoops, that was supposed to be an arrow. Okay, so we still have this nice property of the tangent line having positive slope, but we're bending sort of downwards. All right, so now I think we're all good on that one. Anybody from group 2, Mia and Aaron's row, that wants to volunteer their paper? All right, Michael. All right, Michael has kindly volunteered his paper. And here's about what his paper looks like. His graph looks something like, and that's 1, so looks something like this. Okay. Great. So let's take a look at this first property here. F prime of 0 is less than 0. What that means is that the tangent line to my graph of f at the point x equals 0 should have a negative slope. Well, if I draw on here, at 0 here, I think we're satisfying that. We're going downwards, so we've got a negative slope at x equals to 0. Okay, so first property, we're all set. Second property, we've got f prime of 3 is larger than 0. So if we go out to 3 here and we draw the tangent line there, we can see that we are indeed increasing. So that property is satisfied. And now we want to have this last property. We should have f of 1 larger than 0. Do we agree that f of 1 is larger than 0 on this graph? How would you change it, Michael?
Just like move it up.
Yeah, you could take the whole dang thing and just move it up,
Okay.
right?
Just like f prime of 1, so it's like,
Yeah, so we can just move it right here. And now it looks like we've got f of 1 larger than 0. Okay. Thank you very much. Here's your paper back.
thank you.
All right, last group, there's only 3 of you. It doesn't seem like either any of you guys were super confident displaying your paper, so maybe we'll just do number 3 together. I think it's pretty hard in any case. Let's see here, what do we got? We've got f double prime of negative 2 less than 0. So at negative 2, we should be concave down. At 0, we should be traveling horizontally, or have a horizontal tangent line. And at 2, we should be concave up. There's one function I know which satisfies those properties quite well. And it looks like the function x cubed. Comes up like this. Kisses 0, and then we go off like this. Okay, so if we go to negative 2, negative 2 here, we take a look at our thing here. Whoops. We take a look at our point here. At that point, visually, the graph is bending downwards. Okay, and also, we would be able to tell if we look at the slope here versus the slope slightly to the right, the slope has decreased. Okay, the slope has decreased as we move from left to right. So that's how we can know that we're concave down at that point. We should also have f prime of 0 equal to 0. So that's true because for this graph, the point 0 is an inflection point. Okay, it's an inflection point. And then thereafter, we're concave up. So the last property, f double prime of 2 greater than 0, is also satisfied. So Andrew, Sam, and Alice, did your graph look similar or different than mine?
The same.
Okay, some the same, some slightly different. Okay, I definitely think that one is the most challenging to do. In fact, all of these are kind of high cog, that's what we call it in the teaching world, high cognitive ability tasks. Meaning you really got to think about what you're doing here because it's not an interpretation of something that's already there. You have to really create something new. So these are good problems. This would be a great problem for an exam, as with the next problem, which we're going to do together. Unless there are any questions about these problems here. Okay, thank you very much to Kevin and Michael for volunteering your graphs. It's seriously really helpful. Okay, so problem number 3. We have a function f has f of 3 equals 15 and f prime of 3 equals negative 3 and f double prime of x is larger than 0. In other words, we're concave up. for all x values which are larger than 3. Okay, so let's draw a graph. What we're saying is that so if this is 3, f of 3 is 15. To the right of this red line, we're concave up. And the slope of the tangent line at this point is -3. And we're supposed to decide whether it is mathematically possible for f of 6 to equal 3, or f of 6 to equal 6, or f of 6 to equal 10. Okay? That's what we're supposed to decide. Okay? So, here's the key idea in this problem. I'm going to extend this tangent line a little bit. Do I have time? Yeah, I have time. We're going to extend this tangent line a little bit, like this. Okay, and maybe here's 6 here. Okay, and if I were to draw my graph in pink here, I don't really know what it looks like. The only thing I know is that it's sort of going in this direction at the start, and it's concave up. Okay, it's concave up. So it might look something like this, or it might look something like this, or something in between. We're not really sure what f looks like. But we know it's concave up. And using this information, I can tell you what it doesn't look like. I'll draw in blue what it's impossible for this graph to look like. It can't look like this. Can someone tell me why the graph can't look like that? The blue line couldn't possibly be the graph of f. Yeah, Kevin?
It would be concave down.
Yeah, it's concave down. And they told us that after x equals 3, we're concave up. Okay, in fact, what it means is the graph of f cannot coincide with or pass underneath the graph of this tangent line at this point. Okay, there's no way for me to cross it, because otherwise I would have to be concave down at some point. And that would contradict the information that we've been given. So, what this problem boils down to is deciding whether the points 6, 3, 6, 6, and 6, 10, we want to decide, are those underneath this tangent line, on this tangent line, or above this tangent line? If we're above the tangent line, then it's theoretically possible that our graph of f could pass through those points. If we're below, well, so sorry, we're not going to be able to make that happen. Yes, Kevin. Not Kevin, Ryan. Sorry.
So you just got the tangent line from the f prime of 3.
Exactly. Now, we don't exactly know the equation of the tangent line, which is what we're going to have to do next. Okay? Remember the tangent line equation. Might run out of space here. We've got t of x equals, I suppose it might be a little too much to ask for someone to remember the formula this soon, but it's f of a plus f prime of a times x minus a. So, if I want to know what's t of 6, t of 6 is going to give me the height of this point, which is going to be 6, comma, t of 6. So let's go ahead and plug in. We know that f of a is 15. plus f prime of a, that's negative 3. So really we should have minus 3 times, well, if x is 6 and a is 3, we've got that. So we get 15 minus 3 times 3 is 9. So t of 6 is equal to 6. Bam. Okay, so I'll replace this t of 6 in here with a 6. So this is the point 6 comma 6. And they're asking us, can we pass through 6 comma 3? Well, if I were to put 6 comma 3, ooh, that doesn't show up well, does it? We'll put 6 comma 3 in as a purple point. That's this point right here. Do we think our graph can pass through that point? No, because we would have to pass beneath this tangent line, in which case we would have to be concave down for some period of time, which we know doesn't happen. So A is out. We'll use brown to do 6 comma 6. So 6 comma 6 is actually the point on the tangent line. Could we pass through that point? The answer is actually no. And here's the key piece of information. Let me draw your attention to this greater than sign here. It would be possible if we had greater than or equal to. Okay, it would be possible if we had greater than or equal to, which in some calculus courses, you will find the definition of concavity has a greater than or equal to sign. In our book, it has a greater than sign. Okay, it's a small distinction, but what it's really saying is that if f double prime is equal to 0, well, that's a straight line, and they say a straight line has no concavity, basically. It's a decision that the book makes as opposed to saying a straight line is both concave up and concave down. Okay, so that's just kind of a minuscule difference between some books that you'll see. Our book uses this greater than notation. So in our case, it's actually not possible. All right, how about 6 comma 10? We'll do that with green. That's some point like up here. Do we think f could pass through that green point? Yeah, the answer is absolutely it could, because we could draw a concave up curve here, which passes through that point and satisfies the tangent line property and the property that f of 3 is equal to 15. So this one is possible. Rest of them aren't. Okay. Are there any questions about this problem? Yes, Ellie.
Where did you get the value for f prime of a?
Great question. In this case, a is equal to 3. So this was something that we covered in the last lecture about tangent line approximation. So if we have this t of x here formula, this came from the last lecture. This is the tangent line to f at the point where x is equal to a. So a came from right here. It's the x value of the point where our tangent line starts. So a was equal to 3. So f prime of a equals f prime of 3. So the value of f prime of 3 came from right here in the problem where it says f prime of 3 is equal to negative 3. That's a great question. I kind of just went straight in on this formula, and you guys are definitely going to need to practice with those tangent lines a little bit before you get comfortable enough to just throw it in like that. Okay, it's 10:29. I want to really quickly describe one thing about concavity with tables. It's going to take like 2 seconds. What it really says is if the rate of change seems to be increasing, this tells us f double prime larger than 0 and tells us concave up. If rate of change seems to be decreasing, that's telling us f double prime less than 0 and concave down. So in other words, if I looked at this table, I can see initially the snowfall is growing very slowly, but after a while, these jumps start to get larger and larger. That's telling me that the rate of change is increasing, just telling me that if I were to draw this as a graph, it might look like a concave up graph for that part of the table. All right. Still done. 10:30. We're good. If there's any questions, you can stay after class or come to office hours from 11 to 1. I can't stay for too long after class today. Yeah, Sam.
You just scroll down.
Oh, yeah, sorry. Is that better?
Yeah.
What time did he say the office hours were?
They're from 11 to 1, so it'll be in the MTC room, so you can find the link on Blackboard.
Okay. I can like bring a homework question in there?
Yeah, absolutely. Yeah, I'll help you with any homework questions that you have. Yeah,
Okay. Thank you.
yep, no problem. Do you have any questions, Sam?
No, I'm all good, thank you.
Okay.